Okay, so we're going to start with a little math review. Some of this hopefully should be really easy to you. Some of it might be a little new, but this is definitely stuff we need to know how to do to be successful in this course. All right, we're going to start with just a little bit of units. The fundamental units are what we call the most basic units, the most basic types of measurements that we can make in the world. There are many. We will start out with really the first most common three that we'll use, which are length, mass, and time. Really can't get more basic than that. Now, we call these the fundamental units. There are, of course, specific units we could call like the SI units or just the English system units. You can come up with a bunch: miles, inches, feet, whatever. For length, kilometers would certainly be metric, and we will deal mainly with the metric system. Mass, we really don't talk about that much in our everyday lives. Please don't think pounds is mass. Pounds is a weight unit, which is based off of mass. But the US sort of English measurement for mass is actually the slug. So that tells you how often we talk about mass in our everyday lives. We will more commonly use, of course, grams, time, seconds, days, hours. You can think of ways to measure time. Derived units are based off of the fundamental units. Like I said, there are more than those three. But dealing with those three for the moment, of course, you could talk about velocity, which is really a length divided by a time. Regardless of what unit system you're using, it's still a length divided by a time. So that is a derived unit is based off of the fundamental units. In the metric system, we would commonly use meters per second. Standard metric units. Density is another one, mass divided by volume. And even volume itself is a derived unit because volume is based off of a fundamental unit. Volume is a length cubed. Even if we're talking about liquids, really it is, a length, width, height measurement, which makes that unit derived, and the whole density unit is a derived unit. So if I ask you on a quiz, for the fundamentals, make sure we're discussing length, mass, and time. Not anything more complicated than that. Okay, so in the metric system, the standard SI metric units for length, mass, and time are the meter, the kilogram, and the seconds. Kilograms is not a base metric unit, but it is the standard metric unit that we will use. Grams, of course, will be the base, but we will constantly base things off of a kilogram, which is about 2 pounds. Okay, and one nice thing about units is they work the way variables would in an algebraic equation. So sometimes if you're not 100% sure you have the right equation, you can figure it out if your units end up working out to be what you want them to be. If you're solving a problem for distance and your units work out to give you seconds, something went wrong with your equation. So sometimes it is nice to use units to figure out if our equation is correct. So anyway, algebraic, solving of equations, simplifying our orders of operation, we'd always solve anything in parentheses first, then deal with exponents, multiply, divide, add, subtract. Hopefully we know this. And of course we would work left to right. Okay, so let's work through a couple examples together. Number one, 7x plus 3x. Okay, this is exactly something you'd see in algebra class. X is your variable. They're the same variable, so you can certainly go ahead and add those together. Number two is just like that. Now we have meters instead of a variable, but units work exactly the same as a variable would. So it's the same unit. You can, of course, go ahead and add those up. So that would be 5 meters. Number three, if you have the same variable times itself, of course, we would square that. And, of course, 7 times 3 is 21. All right, so the same thing here with number 4. Like maybe this is an area measurement of a room, 2 meters by 3 meters. What's the area of the room? Well, we would say 6 meters squared. All right, now dividing. These are still all units. We got meters and seconds. Now these are two separate fundamental units, so we can't really combine them in any way. We can, of course, do 10 divided by 5 and get 2, but as far as meters divided by seconds, we just have to leave that as meters per second. All right, just like if you got x divided by y, you can't simplify that further than that. All right, this would be sort of an uncommon case for us, meters divided by meters. Units would cancel out here. If you had 10x divided by 5x, the x would go away. So an unlikely case where you'd have no unit on your answer at all, but that would be the answer there. Perhaps that's some ratio. All right, and then 10 inches divided by, or sorry, plus 5 meters. Can do it. We haven't gone over conversions yet, but at the moment, I would just sort of leave it as is. Can't really make that any more simple unless you go into some unit conversions with inches and meters. How do we do? So that last one can't simplify without converting. All right, number 8. What if we have a longer, more complicated function or problem to solve? All right, we got to do orders of operation. We want to work left to right, but you've got to follow orders of operation. So please don't try to do the 6 plus the 4 first. Multiplication comes before addition. So we would really have, for this particular part, just 2 meters per second. And then I want to add 6 meters to that. But that's about it. You cannot make that more simple. So that's answer number 8. Number 9, all right, I see some parentheses, definitely going to work there first. 6 meters minus 2 meters, sure, I can do that. 4 meters. Next, I will work with a division. All right, even though it might be really nice to just say, okay, 4 meters plus 8 meters, I can combine that, but got to follow your orders of operation. So 8 divided by 4, we got 2. And then meters per second. And that's really about it. We could maybe factor out a 2m if you wanted to. I'm not really particular about that, so long as the final answer is the right answer. It doesn't necessarily need to be the most simplified version. So if I took out a meter, I wouldn't really have a unit here. I just have sort of per seconds, which you could also write as s to the negative 1, or even hertz when we study waves means per second. But like I said, I wouldn't really worry about the blue there. Okay, scientific notation. I know we did this in 9th grade, so this hopefully is not a big deal. It's just a way of representing really big or really small numbers. We got 110,000. I can represent that, as something times 10 to the something. That's your scientific notation. Leading number has to be between 1 and 10, so don't make it 0.11, don't make it 11. It's got to be between 1 and 10. 1.1 times 10 to the, and then however many times we move that decimal place. So that would be 1, 2, 3, 4, 5. 1.1 times 10 to the 5th. All right, small numbers, just make sure your exponent is negative. Okay, moving my decimal 1, 2, 3 times, but 3 times to the right. My leading number is now, of course, between 1 and 10, so 10 to the negative 3. To convert out of scientific notation, just use your common sense. A negative exponent is a small number, so make sure you move your decimal the right way. A positive exponent would be a larger number. So move the decimal to the left for negative exponents because, again, we want these two numbers to be the same thing. So to get back to what I started from, I definitely need to go left. course, right for positive. So here, that's obviously a small number, negative. Move your exponent to the left. 0.000123. Okay, and another way of using scientific notation without actually using the 10 to the whatever exponent is with our metric prefixes. And here is the list. In 9th grade, we really just stuck with kilo to milli, for the most part. But there are, of course, some bigger and some smaller metric prefixes. We will use some of the smaller ones when we get into electricity. But for the most part, we're really just going to use milli, centi, and kilo. So if you know those three, you should be pretty much good to go for 3/4 of the year at any rate. To use this chart, though, and this chart is on the wall as well, as you can see, but to use this chart, we always put the 1 with the prefix and then the multiplier with the base. So for example, centimeters, maybe something we know. Okay, 1 with a prefix, so 1 centimeter would be 10 to the negative 2 meters. Or kilometers. Kilometers is a big unit. 1 kilometer is 10 to the 3rd meters. And when I say, the base is that like single letter unit, like just M for meters. As soon as I stick a letter on there, km, that's the prefix. So 1 kilometer is 10 to the 3rd meters. Here are a few other units that we really won't use too much. Every once in a while we'll see something where we need to convert from the US system to the metric system. But 1 meter, and this is just kind of good general knowledge anyway, a meter stick is about 3 feet, 3.28 feet. 1 kilometer is 0.62 miles. So if you've ever run like a 5K race or a 10K race, you are not running 5 miles if you're running a 5K. You are running less than 5 miles, you're running about 3.1 miles. 1 mile is 5,280 feet, and 1 mile is also 1,760 yards. All right, so use dimensional analysis to convert. So we do need to know how to convert units. Hopefully you've learned that in chemistry, physical science, somewhere along the line. If you need help with this, it's something you're going to need to talk to me ASAP about. But here's one quick example that hopefully you've seen before. All right, so 10 inches to millimeters. And then, before you even begin, you should maybe have an idea in your head, is this number going to be bigger or smaller than 10? All right, we'll have an idea of a millimeter. There are 10 millimeters in a centimeter. They're the ittiest little marks on a ruler. So there's probably going to be more than 10, millimeters in 10 inches, obviously. So to do dimensional analysis, start off with your given number, 10 inches, times sign, fraction bar. And here is where we come up with just some sort of relationship that is true because, and we need the top to equal the bottom, because, well, just as a quick aside, if you were doing 10 inches times 1, does that change anything? No, that's still 10 inches. Okay, well, what if you had 2 over 2? 10 inches times 2 over 2. Well, 2 over 2 is 1, so you still have not changed anything. And that's the idea behind dimensional analysis. I can multiply a value by 1,000 fractions and not change anything so long as the fraction really equals 1. So to make that true, the top always has to equal the bottom. So the first thing you want to do is, of course, put your given unit in the denominator of the next fraction. I want to cancel out inches. Just like variables could cancel, units can cancel too. And now I just want to use something useful that I know that will help me get to millimeters. Looking at my chart, I don't see inches on here, but you guys know something about inches, and that is probably that 12 inches equals 1 foot. So here I'm multiplying by a fraction, but this fraction really equals 1, the value 1. The top equals the bottom. 1 foot is the same thing as 12 inches. So I'm going to end up changing the unit, but I've not changed the value. I've not changed this amount of 10 inches. All right. So I said units cancel, so I now no longer have to worry about inches. I'm certainly not done, because I'm only in feet, and I want to get to millimeters. So just keep throwing in fractions as needed. I've got feet now. I want to get rid of feet. So what do I know about feet that's helpful? Well, I've got this lovely chart. I know that 3.28 feet is 1 meter. So I can put 3.28 on the bottom, 1 meter on the top. Now I've canceled out the unit of feet. And I'm now in the unit of meters if I were to do this math. So I'm almost there, and now I want millimeters. So 2 options really. Use the prefix chart, like we just said. We said that 1 goes with the prefix, and that the multiplier goes with the base. Let's see if I go back 1 second. So if I go back 1 second and I find my milli, all right, milli is a factor of 10 to the negative 3. But that means the 10 to the negative 3 is the multiplier of the base. So if I want to use the metric chart, I know meters has to be in the bottom. Remember, your units are always canceling diagonally. And I want millimeters on the top. But for some reason, students always like to mess this up. Where does that 10 to the negative 3 go? Does it go to the top? Does it go to the bottom? Well, one more time. The 1 goes with the prefix. So 1 little bitty millimeter is 10 to the negative 3 meters. All right, and then we are done. Meters cancel, and I'm left with millimeters. I need to do this math. I need to do 10 times 1 times 1 times 1 divided by 12 times 3.28 times 10 to the negative 3. But I wanted to show you one other fraction because I said if you knew centi, milli, and kilo, you didn't really need to worry about that chart anyway. So I still want meters in the bottom. I still want millimeters up top. But now, what is the relationship between meters and millimeters? And milli and kilo are both factors of 1,000. Centi is a factor of 100. But now you got to put that 1,000 in the right spot. Does 1 millimeter equal 1,000 meters, or 1 meter equal 1,000 millimeters? And it is the second. Okay, so sorry to drag that problem out, but that is how you do dimensional analysis. Like I said, now you just multiply across all the tops. So I've got 10 times 1 times 1 times 1,000. So I've got 10,000 on the top. And then on the bottom, I've got 12 times 3.28 times 1. Which is 39.36. Come back up and divide that. And I get about 254, some decimal place digits there. Nice thing about this course is we really don't have to worry about scientific notation, significant figures. So I don't have to worry about exactly how many digits I'm supposed to have. Just don't be unrealistic about it. You know, if your number only starts with really 1 significant figure, don't give me 300 significant figures in your answer. But I'm just going to leave it as 254, and again, the final unit was millimeters. Voila. Okay, as far as solving equations go, a full equation where we have an equal sign. Some of those previous problems we didn't have an equal sign. Move all terms with the variable you are solving for to the same side. Hopefully this is just algebra review for you. Occasionally we might need to factor out some terms. If you're solving for x and you have x in many different places, you can combine them and factor perhaps. Please don't try to solve for a variable in the denominator. You've got to get any variable you're trying to solve for out of the denominator. And of course, whatever you do to one side of the equation, you have to do to the other. So I am hoping we already know how to solve equations and solve for a variable. There is a practice sheet for you to work on with just a variety of random equations, but really those equations are set up like physics equations we will see, and I'm going to ask you to solve for just different variables within those equations. You should be able to solve for any variable in that equation. Alright, and then lastly for our math review, just a little trig review. We will do triangle math a lot in this class. So trig is, of course, a branch of math that deals with the size of a right triangle. So it does have to be a right triangle, which means, of course, there's a 90-degree angle in there. I think we know this general info about a right triangle. C would be the hypotenuse. So we're going to do trig, sine, cosine, tangent, and also Pythagorean theorem, which I know you definitely know Pythagorean theorem. A squared plus b squared equals c squared. We can use this only to solve for sides of a triangle, though, no angles here. Okay, so two quick examples. Right triangle, you want the hypotenuse. Okay, so that's your C. Just remember your last step is going to be to square root. And I'm pretty sure this answer is 26. Okay, occasionally though I see students mess up a problem like this. It says the hypotenuse is 169, so we'll pretend that was 169 centimeters. One of the right sides is 119 centimeters, maybe bottom. What is the length of the other side? Okay, still use Pythagorean theorem, but just realize you're not solving for C this time. You already know C, you already know the hypotenuse. So like I said, sometimes students just always try to find C. So this would be 169 squared equals 119 squared plus b squared. Calling this side b. So make sure that there's some subtraction in your problem when you are doing this. 169 squared minus 119 squared equals b squared, square root both sides. And I am pretty sure that answer is 120 centimeters. So hopefully common sense, but do bear in mind you're not always solving for the hypotenuse. Okay, and now on to the trig functions themselves. Sine, cosine, tangent, which we can use to find a side or an angle of a triangle. We will definitely use angles of triangles as well. So if you want to find the angle, you have to use the inverse trig function, which all your scientific graphing calculators have. It's just got like sine to the little -1 means inverse. And then, watch whatever units you're in. For most of the year, we should be in degrees. But we will deal with some radians towards the end. All right, so sine, whatever your angle is that you're given, is going to be sine of that angle is opposite over hypotenuse. So if this is the given angle, the opposite side to this angle is, of course, the one farthest away. That's completely opposite to it. It is not creating that angle in any way. And hypotenuse is always the hypotenuse. So sine is opposite over hypotenuse. Some of you guys know SOHCAHTOA as a way of remembering that, which is sine is opposite over hypotenuse. That's a sa. Ka. Cosine is definitely going to be adjacent over hypotenuse. And TOA, tangent, would be opposite over adjacent, SOHCAHTOA. So I'm just going to make up some numbers real quick here. Let's say, for example, let's make this an angle one. I am given two sides. I know that this side opposite the angle is, let's say, 25 centimeters. And the hypotenuse is, 40 centimeters. What would the angle be? All right, so this would be an inverse trig function. We would want to say sine inverse of opposite over hypotenuse equals the angle. And really where that came from was, you'd want to get the angle, you're trying to get angle by itself. Well, if I want to get the angle by itself, I've got to get rid of the sine function. To get rid of the sine function, I need to do inverse sine, but I've got to do it to both sides. Inverse sine of sine, goes away. So now I have my angle equals inverse sine opposite over hypotenuse. Just make sure that you are in degrees, which I am. So I'm going to do inverse sine 25 divided by 40. And please try that on your own too. Make sure you're getting the same thing as me. If you're not, most likely you're just in radians. But 38.7 degrees is that answer. Okay, so that's sine. Let's just do one more of each. All right, so cosine problem. This time let's just say that I know the angle. And let's make it 30. And there actually are some tricks to a 30, 60, 90 triangle. So let's say the adjacent side let's say I want to find the adjacent side. Let's say the hypotenuse is 2. And my angle is 30 degrees. Find the adjacent side. All right, well, I will plug in cosine of 30 equals adjacent over 2. And just like you're solving, anything in algebra, I want to get adjacent by itself. So get rid of that 2. If you're dividing by 2, multiply both sides by 2. All right, so we got that. All right, and I get 1.73. Now, interesting thing is, since this is a 30, 60, 90 triangle, maybe you know this already, but when you have a 30-degree angle in there, the side opposite of that is always really x, or 1. The hypotenuse would be double x, and the other side would be x square root of 3. So in this case, since my hypotenuse was 2, my side opposite the 30 had to be 1, which we didn't solve for, didn't ask for the opposite side, but I know it would be 1, and therefore the adjacent side should be 1 times square root of 3. And you can do square root of 3 and double check that we get that. And of course we do. So 30, 60, 90 triangle is not a bad one to just know. They do often pull up 30 and 60 degrees in problems we'll see. Okay, one last problem, tangent problem. Tangent will be used for opposite or adjacent side. So again, assuming this is my angle, and it doesn't like have to be the top corner angle. It could have been this angle. But if I want to find, what have I not found yet? Let's find adjacent again because I want to find something on the denominator. Let's pretend the opposite side down here is 10 inches, centimeters, whatever. And let's go with an angle of, I don't know, 20 degrees. So set up your tangent function, tangent of 20 equals 10 over adjacent. You can just call it x at that point if you want. Here's, a sad math mistake out of C. You got 10 divided by x. You're like, okay, I want to get x by itself. I see divides. I'm going to do the opposite of that, which is multiply, and I'll just multiply 10 to both sides. No, we cannot solve for x if it's still in the denominator. That doesn't really get rid of the 10 either, but I got to get x out of the denominator. So multiply both sides by x. First step's not really helpful at the moment because x is still next to a term. I did not get x by itself, but I got to add the denominator. Now divide by tan 20. And we get little rounding, but 27.5. And like I said, we'll use the trig functions a lot, so rearranging like this will become second nature to you. And that concludes our review on the math basics.